All right. Thanks, man. I'm doing good. How are you? Give me a second here. There we go. Hey. I'm doing good, Aiken. How are you, my friend? Gonna finish up maths work. Very good. Very good. Hopefully it's pretty easy, or anything I can help you with. Desmos isn't working. You know, I've had weird times this morning already. Like my connection wasn't really working all that well this morning. So I've had to restart the stream at least once. So I'm with you there, buddy. I'm with you there. I have no idea why either. So what you been up to, my man? How to add numbers into Desmos? Just chilling on Discord and Twitch all day? Fair enough. Fair enough. Let's check it out then. Let us check it out. Let me switch to the other screen and let's answer that question together, right? I think I've dealt with Desmos, but Desmos calculator. Wait, I think I have actually dealt with Desmos once. Oh yeah, I remember this thing. I worked with it once or twice. Hey, cool dad. Good morning. Good morning. Aiken, what are you trying to do with Desmos? Are you trying to do like graphing or something? Do like y equals 2x plus 2 or something like that? Hey, Riv Spice, thank you for the thumbs up. I appreciate it. Hey, Goldmash, how you doing there? Anna, good morning to you. How you doing? I'm doing great. I'm doing great. Hopefully this stream will not go down here today. I had a couple issues here this morning with the interwebs connections, but hopefully that won't be too bad. What are you trying to find with X and Y? Line of best fit, Aiken? I just a list of values. I have to check whether the weather temperature every 15 days for the past year and graph it. So just the graph without the line of best fit. I have to check the weather temperature every 15 days for the past year. Okay, well then it's just a scatter plot then. Right? Because it's not a line, is it? So do you have to graph a line? You have to graph a line, or it sounds like just a scatter plot. So all you have to do, Aiken, in that case is just literally plot the points. So because you don't have to put the line of best fit, they just want the scatter plot there. So that you don't need the calculator for that necessarily, though you can technically do it on a calculator. But if you can map it out on a line of best fit, just like putting like the day and then, you know, days as X and then the temperature as Y, then you should be all right. All right, so what does it ask you to do next then if you did the scatter plot? Good morning, Megan. How you doing? How we doing there? You got the second round of vaccine is kicking your butt, cool daddy. Yep, that is exactly what the second round of vaccine is exactly supposed to do. Vaccine is supposed to do that. It's working as intended. Yeah, it's going to be a doozy for the next couple days or so, okay? You took the practice test this morning? Wonderful, Megan. How did it go? So far, so good, I hope? Aiken, get back to me. I want to hear what the next problem has to say. If we want to do the line of best fit, I can do that for you. Oh, then it does want you to find the line of best fit. That part is true. I mean, you took it. Okay. I see. We need to find the linear regression line for that. Okay. Let's do it, my friend. Let's do it. Do it. Do it. I want to see if we can find line of best fit calculator. All right, buddy. I got a calculator for you. You give me the x values and the y values, or I can link it to you. Here, I'll link it to you. And then you can go ahead and give it a go, okay? It's okay. Remember, there you go, Aiken. That's a good site to go to put your x and y values in. And then you'll get your line of best fit down here. Well, Mash, you are very wonderful. And I hope you're doing really well. Saying something nice, nothing wrong with that. Well, Dad, you're an excellent Mario player. You may die too much, but you always keep trying, and I admire that perseverance. That's the one thing I can definitely admit. I can admire that perseverance. Your Discord name is Bibu. Gotcha. Would this give the scatter plot as well? Remember, this is just the linear regression line, Aiken. The scatter plot you already found in the first part. So you already have the scatter plot from the first part there, Aiken, according to what you told me. So this would be like part B, where you tell me what's the model that would best fit that data set. So this is that answers the question that you're asking. Could there be a known function that could model the data, find the function? Well, you're finding the function here by finding the line of best fit, or the linear regression line. Okay. So I gotta ask Megan. How'd you find the practice test there? I know it's a little bit tough, but hopefully it wasn't too overwhelming. I have to ask. Questions are important. I'm sure you have questions over some of the homework there. By the way, I see we changed our name to River Spice. It's perfectly fine. River is River Cat and River Spice. But I hope things are going well with you, my friend. I was doing pretty well. Okay, 6. You know what? It's a practice test, and that's a really good start. You have a really good start there. Oh, okay. You couldn't figure out how to open it up again after you took see what you did wrong. Okay, that's kind of weird. Supposed to be practice. Hey, made you mad. How you doing? I hope you're doing good, my friend. I hope things are cool with you. How are things? What you been up to, my friend? Doing good? Any plans for today? Or just chilling, straight chilling? "15-page paper to edit? Oof. That's no fun. What's your paper on, if I may ask? It worked? Nice, Aiken. All right. Told you, my friend. Told you, we gotcha. Gotcha. Computer and network security. Okay, well, that's actually not too bad. That's actually pretty important, computer and network security. Writing a 15-page paper on that isn't too terrible. 0.92x minus 6.55. Okay, that looks about right. If that's your line of best fit, then that's great. Just make sure you're going out to the proper number of decimal places there, Aiken. So it might ask for a certain number of decimal places, so just be careful about that. I'm telling you, computer network security is going to be a pretty big thing. I'm going to be honest with you, the next biggest thing probably in computing, in all honesty, ladies and gentlemen, is going to be quantum computing. So quantum computers are probably the next generation of moving forward here. When it comes to the computer evolutionary cycle. I mean, right now it's very expensive to have quantum computers, and there's not a lot of applications that use quantum computing. But I think that that's going to be probably the next biggest frontier for modern technology. Yeah, but look, Macon, I'm going to be honest with you. Quantum computing is going to be the biggest thing, probably. Many would lose their jobs. That's probably true. A lot of things are more automated. I'm not going to doubt that for a second. But I think that that also makes sure that, at least in terms of from a humanity's perspective, that you may lose jobs in one field, but that means you pivot to something else in order to compensate. So, which certainly there are things that you can do, you can pivot to compensate for job losses in certain fields, for making for automating other fields. So, I love Tesco's. So I don't know if you guys seen this before. Well, I'm sure you guys have heard. I'm sure you guys have heard of Amazon, the Amazon Go store or something to that effect. Has anybody heard of that? Right? The Amazon grocery store or Amazon Go store. Yeah, I could bring it up here. You've heard of it? Okay. Yeah, the Amazon Fresh store and the Amazon Go store. So the Fresh store is where they have their big grocery store there, Kristen. And then the Go store is like the mini store. Yeah, kinda. So there's two parts, right? I think there's the Amazon Fresh store, the big grocery store, and then Go store is like their mini store, right? And that they don't have like cashiers or anybody really monitoring anything in the store. They just have like the stock of stuff, and then they automatically charge you when you walk out. Maybe I'm wrong about the Amazon Fresh store because that could be very different. But for the Amazon Go store, I should go to the Amazon Fresh store down the street. This is literally down the street, but I haven't been in there yet. Um, but yeah, that may be the next thing for grocery shopping and whatnot. Um, and for let me go ahead and do this. Let me go ahead and do this here. Let me go ahead and show you why I believe. Go over to the YouTube. The YouTubes. Oh my god. All right. That's true. But what we're going to do here is take a look at the you have to find the max and minimum of the variable with this function now. Oh.
For most of our history, human technology.
Let's take a look here at a video which explains it in just a brief detail, brief synopsis. Obviously, this doesn't go into super great detail, but it does give you a good overview about what quantum computers actually are. So, um, like it says in a nutshell, is probably the best way to put it. So, like, some people probably have heard of it, but they may not know exactly why it's so important in the first place. So, some of you
Technology
have,
consisted
but
of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. Four classical bits can be in one of two.
So it does sound very confusing. Okay, so I'll stop here for just a second. It does sound super confusing, but think of it this way. If you go back, basically the one qubit is in both states at the same exact time. It's either a 0 or a 1 at the same exact time. Once you stop it, then it can take on either one of the two positions. So that's one of the biggest things about quantum computers compared to what we have with regular computers. With regular computers, it's a 0 all the way through, or a 1 all the way through a whatever calculation that you're doing. In a quantum computer, um, it can take either state at any time. So it's not necessarily 0 all the way through or 1 all the way through. So that's the biggest difference between a quantum state, a qubit, and a regular computer. So is a normal PC quantum? No. No, not at all. A normal PC is very, very standard. It's like, okay, I got one transistor. It's a 0 or 1 I can push through, but I can only go through it one at a time. Imagine if that electron that goes through that transistor can be both 0 and 1 at the same time. Then that's a quantum state. Essentially, to kind of break it down into something super simplistic, that's essentially what you're doing there at the end of the day. So, not even double the speed there, Aiken. You're talking about exponential speed, because now now it's not just double the speed, you have exponential states that can occur between different qubits, as you'll see here later in this video. So that's the biggest thing why quantum computers are kind of like the way of the future. You could take we could take our boxes that we have right now, right? Our computers, our desktops, our laptops, or whatever, and then exponentially put it up by however many qubits there are, and that's how fast that thing will go. So it's crazy. It's pretty crazy how fast they can do calculations with qubits in comparisons to the current computers that we have with current architecture. Quantum computers are currently only used by governments or by companies like Google has a quantum computer, for example, to run search algorithms and whatnot. So it's used for a limited amount of things because we don't have many applications that can work with it right now. And of course, with quantum computers, or just like computers that has a lot of processing power, you need to have it in very strict controlled environments in order to actually do that. So not only is the technology currently really expensive, but the environment that you have to store it in is also very expensive as well. So hence, it only makes sense that only certain organizations can actually have access to quantum computers at this time. But it's starting to get more and more prevalent within the community about where it's starting to get more and more prevalent where making these quantum computers could be more commercially viable within the next 5 to 10 years or so. So, if scientists start to figure out exactly how to make this commercially viable, you can start selling it on the market. Then maybe in the next 5 to 10 years, you may see that actually be available on the retail side. I don't, I mean, you're talking about taking from our standard computers and then exponentially rocketing everything up. Take Moore's law and then basically throw it out the window, put it at an exponential scale and basically just destroy. It could literally destroy anything. Like you could take a quantum computer and it'll literally destroy any supercomputer that we've had in the past 30, 40 years. It doesn't matter. It's that crazy. Um, Absolutely nuts. Oh yeah, right. I got to do that here really quick, by the way. I totally forgot. Give me a second. I got to remember here. Okay, let me go back here and then I'll go back to the video. Okay. I got to do a little bit of intro here and then I got to do a little bit of an intro and then I got to ask some questions. All right, so give me a second here. Okay, let's get started today. Welcome back to Wednesday, end of the week time today. So today, ladies and gentlemen, is more Q&A for some statistics. So I've forgotten my day job. I promise you that. I haven't forgotten my day job. We'll finish the video. I promise you. But first and foremost, here are questions over anything for stats. That's the first and foremost most important thing. Again, I have not made up the final here yet, by the way. I'm just going to point that out. I will be making up the final here eventually this weekend, but I kind of have a good idea about what I want to do in terms of questions. I like probably I've mentioned this last time, but I'm thinking like 40, 50-ish questions here for the final. I think would be probably fair. So kind of because it'll be a kind of like a combination of all three of the exams put together. So that is kind of like my idea. So I'll have to spend a few hours kind of putting that together there and seeing kind of chopping down questions to getting into an appropriate length of which you can finish it in an appropriate amount of time. So it's not like super crazy. So that's where things stand at this moment in time. You also have the homework there that's also due last day of course. All right. Does anybody have any questions, by the way? You figured out open to Oh, you did? Okay, good. Good, Megan. Woo! Did you have any questions there? Uh did you have any questions there? By the way, anybody have any questions from the homework or the test or practice test or whatever? So you guys can take your time here. I'm gonna go back to the video here while you guys are
2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once.
All right. So if you listen to what it just said here, let me go back here for just a second. This is why it's exponentially crazy. Let me show you.
4 classical bits can be in one of 2 to the power of 4 different configurations at a time.
So our classical computers that we have can be in 16 possible combinations, but you can only choose one out of the 16 possible combinations if you have a 4-bit computer, for example. All right, so this is 2 to the 4th power. You have 16 possible combinations, but only can select one of those 16 to actually do calculations with at a time.
That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once.
So now with 4 qubits instead, you can take on 16 with those 4. You can take on literally 16 at the same time, because all of them can assume each one of these values at the same time, which is pretty crazy.
This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. But a quantum computer with exponential speedup could do it in a breeze. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures, such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. This video is supported by the Australian Academy.
So essentially, at the end of the day, the big thing is that it's looking more and more. It's looking more and more that quantum computers are going to be probably the way to be, from what I've read over time. This came out in 2015. It's been 6 years since this video came out, and the technological field of has come out better and better over time. Well, that depends, Cool Dad. It's all dependent on if you have better encryption. So if you have pretty good encryption, if you encrypt using quantum data, then that's fine. Quantum computing, you can do that as well. Let's see, Megan, I know you put something down here. So for number 1 and number 3, I missed the P of X stuff. Okay. So number 1 and number 3 there, respectively. Oh, let's go ahead and take a look. Let's take a look at that. Let's be all nerd stuff together. Let's be nerds. Nerds are the best, man. Okay. All right. That was from chapter 9, right? Oh, oops, that is the homework. Yeah, full from the practice test there. So all right, so let's go over you can do the practice test as much as you want, by the way, so matter. Okay. Oh. Wonder why I can't see anything. I have my dark reader. I have to switch to the light. The light, I tell you. Okay. All right, here we go. So a simple random sample of size n is obtained with a population of mean of 66 and a standard deviation of 16. All right, what must be true regarding the distribution of the population in order to use the normal model to compute probabilities involving the sample mean? All right, assuming this condition is true, describe the sampling distribution of x bar. Assuming that the model can be used to determine x bar being less than 69.7, being bigger than 67.2. All right. What must be true? You must have probably letter B here. Okay. Now the most important part here for you, Megan, is this second part here. All right. The second part here is the big crux to the problem here, because if you get this second part right here of this part A, then that'll help you with the last two parts here to finding the probabilities. So for example here, it says, okay, well, what's the mean and standard deviation? Well, we have a sample size here of 10, all right? And, right, okay. So we have a sample size here of 10, but the standard deviation is what is different. So the standard deviation is going to be, remember, for a sampling distribution here specifically, that's going to be equivalent to the standard deviation divided by the square root of the sample size. So that is going to be letter B here. Okay, so this is, like I said, the most important part here as part of this problem here specifically is going to be that guy right there, because that's going to set us up for parts B and C here respectively. So the standard deviation divided by the square root of the sample size is what you want there. So I want 16 divided by the square root of 10 for that particular part. Okay. So then why do I need that? Why do I need that in particular? Why does that need to happen? Well, the reason why that needs to happen here is because in order for me to get the correct probability here, what I need to do is I need to use my normal CDF function. Now, I know it's been a while since you've used the normal CDF function, all right? But remember that to get to our normal CDF function here, we go second and vars. Okay, so remember we go back to normal CDF. We have a lower and we have an upper. Okay, so our lower value here is, if you see here, this is x is less than 69.7. So that's, remember we used this a long time ago, but I know it's been a while, but we're going to use -1, second in the comma key to get that little letter E to the 99 power, right? That'll reflect like minus infinity on our calculator there. Our upper will be 69.7. Our mean here is what we have here in letter, this part here, which is 66. And, sorry, 6. And then our standard deviation here specifically is going to be exactly what we put down here in letter B, which is 16 divided by the square root of the sample size, which in this case is pushing buttons that I don't want. 16 divided by the square root of 10, and remember, close it off. And then we want to hit paste. So this is what we should have here as our numbers here respectively. So, and then we want to hit enter on that. And so here we get 4 decimal places, so 0.7677 will be our first one here. All right, so that's the first part there. Now, if you want the probability of the second one here, probability of x is bigger than or equal to 67.2, we want to repeat the same exact process here. So second in vars here, going to normal CDF. This time, though, since it's bigger than or equal to, we're going to hit 67.2 as our lower. Our upper here is going to be positive infinity, again, as far as positive infinity means on a calculator, which is 1e to the 99. And keep the other two values exactly the same, 66 as your mean and 16 over the square root of 10, just like you had from part B. And so we want to hit paste on that. And then here in this case, we get 0.4063. All right. And these two here will be our answers for parts B and C here, respectively, for number 1. Okay, any questions about that? Hopefully that makes it easy. Question mark? I'll just move forward. All right. And you asked about number 3 as well. Okay, so you asked about this one as well. Okay. All right, so for this one here, specifically, let's talk about this one here, Megan, for number 3, because that's a little different than what we did here for number 1. So in number 1, we dealt with like a sample size and a mean and a standard deviation. In this case, we're dealing with a p, a proportion. All right. In this case, a population proportion. Are the rest of the classes going to be this kind of miscellaneous review? I mean, yeah, but I mean, if you don't want answers to your questions to help you pass the test, I don't know what else to tell you, cool dad. I mean, it's going to be review. But anything that you've forgotten, remember, the final covers everything. So, miscellaneous review is kind of important. I know why you asked that question, though. Okay? Like, you don't have to lie to me, cool dad. Like, I don't even need to be there physically next to you about why you asked that question, cool dad. All right. The answer to why you asked that question there specifically is that if I say yes, then that would be like, oh, well, I can go and stream some more Mario Maker while I kind of procrastinate until the very last minute, and then I come into your stream and be like, I'm going to use some cargo shorts for drag your ass back into my stream, and have you actually review crap that'll actually be helpful for your grade. That's to tell you that's what I'm gonna be. Essence. that, that question just basically leads to that conclusion. I'm gonna use your channel points against you. I'm going to drag you back here. I'm gonna make you go over stuff that you didn't roll from before. Make sure that you get a better grade. That's pretty solid. I'm sorry. Uh, wait, and that's not how it be. Ho ho ho. Wait a second here. Wait a second here. That's pretty salty. Remember, I'm here to help you. I'm just here to give you a friendly I'm here to give you a friendly reminder that even if it's the same type of class here for the next 3 weeks or so, it doesn't matter. I'm trying to help you get your better grade at the end of the day. It's important, you know? We want to be able to get you a better grade, all right? That's what I'm trying to do, anyway. All right, let me go back here for just a second. All right, so here we have a population proportion here, Megan. All right, so in this case here, how do we go ahead and find this guy out? Well, this first part here is going to be the most important part here. All right, so what we want here is if we were to describe a sampling distribution for a population proportion here, Megan, then we need to first look at P, which is 0.24. As you can see here, all three answers are 0.24. What it comes down to is, of course, the standard deviation, and we're going to use a specific formula in relation to the standard deviation. So let me just bust this out here for just a second. Where are you? There you are. There you were, and then you weren't there. There you go. So specifically here, with number one, we used the, again, we used this guy here. This was the standard deviation. All right. So this is the population standard deviation. All right. Now, in this case here, what we're going to be using for number three is the standard deviation here. In our case, in this case, is going to be this guy here. This was the square root of p times 1 minus p divided by n. So we had this this particular guy here for number three to get our standard deviation. Now, if we follow suit with what p is and what n is, we're just going to go ahead and plop in some numbers and see what we get. So essentially, we're going to have p here, which is going to be 0.24 times 1 minus 0.24. And divide it, so the square root of all that, and then 1,000 here. So again, make sure to not enter this into the calculator incorrectly. Remember, you do need to go ahead and figure out what's inside of this guy here first, and then take the square root of that whole shebang. Okay. Hey, Boots. Thanks for the math, Twitch. Have a good rest of the semester. Hey, Boots. Thank you very much. I appreciate it. Hey, that's what I'm here for. I'm here for math. I'm here for mathematics and some fun. Yeah, so go back to those sections there. Remember, I put those questions in order, so you could go from like chapter 9. You could go from chapter 8, 9, 10, and 4. So this is from chapter 8. Go to chapter 8. This is in that first section from chapter 8. Now, the TI Inspire is way overkill for what you do most of the time. If you're doing calculus, though, it's super helpful. I ain't gonna lie. So let me figure out what this guy is here. Make sure you can replicate this same thing here, by the way, Megan and Cool Dad. So I get 0.0135 is what I get here when I take the square root. So I should have this first one right here. Okay, so if you enter this into the calculator here correctly, you should get 0.0135. My school made everyone buy the TI Nspire. Holy crap. They don't allow TI, actually technically, my school doesn't allow TI Nspires because they're too powerful of calculators. Because like in calculus, for example, you can literally find derivatives and integrals just using the TI Nspire directly. So it's like, even if you want to go calculus 3 by Nspire, you could do like triple integration and it'll do it in your stead. All right. So if you got that there, they do test mode on it during exams. Okay. I mean, I totally understand that. It's just like it's probably the strongest handheld calculator on the planet, no question. Um, all right. So for letter B here, you do the probability of x is bigger than or equal to 260. So in this case here, because now we have our values that we want here from this first one, letter A. So what we have here is we want to do the same thing we did last time here. We're going to do normal CDF. All right. We're going to pick a lower and upper here. So this is bigger than 260. So we'll take 260. 1e to the 99. Our mean here is going to be 0.24. Actually, I should say here, x is 260. Let me see. Oh, actually, I forgot. That's actually fairly important here. Let's, right, we're talking proportions here. There is a significant difference. Let me go back for just a second. Stop the presses. All right, so because it says x is 260, x is bigger than or equal to 260, it does imply one thing. We did a sample size of 1,000, right? That's what we did here. And so because of that fact, because I'm going too fast technically, what they want you to do is first figure out what's 260 divided by 1,000. So if you do that, that's going to be 0.26. So what you're really figuring out here for part A is what happens if x is bigger than or equal to 0.26. Okay, that's really what you're figuring out here for this part here is x is bigger than or equal to 0.26. Okay, so although it says 260, while that's true, there needs you to use the actual proportion here to actually do the normal CDF stuff. So we're actually go back to normal CDF. Our lower here is going to be 0.26. Our upper is going to be 1 because all we're dealing with is proportions here specifically. So we're going up to 100% max. So we don't need 1e to the 99. We just need 1 for 100%. Our mean here will be 0.24. And then we'll just put in our standard deviation we found from the first part there is 0.0135. And then we'll go ahead and paste that in. And so here we get 0.0692. It'll be our first one in there. Okay. And then for the next one, it says x is less than 210. Well, again, you could do 210 divided by 1,000. So that's less than 0.21. So here we're going to go normal CDF. We'll go lower is 0 up to 0.21. Again, 0 to 100%. That's all we care about. And we could keep the other two the same. And so here we get 0.0131. Okay, and there we go. We got our answer for number 3. All right. Any questions about that? I could have sworn there was a radio button. Well, oh well. Oh, all right, cool. If you have any more questions, please feel free to ask. Put a little music on. Anybody else got any more questions? Please feel free to ask. Aiken, did you figure out all the parts to your problem there? What's my favorite breed of dog? Ooh. Man, that's a great question. I like a lot of different types of dogs. I love a lot of the... I like the, really like the Labradoodle. Labradoodle's really good, or the... You got 21 wrong? Okay, 21 says the given data represents 10 randomly selected CEOs in stock performance. Analysis data sets the correlation coefficient of that. Alright. What will be the predicted stock return for the company whose CEO made 15 million? The predicted return for this company made 25 million. Alright. Okay, so here we have the compensation, and then we needed to figure out the... Right, okay. Alright, so all they want you to do here, Megan, is all they want you to do here, Megan, is to find the line of best fit. Oh, okay, working on the same problem? Good, then we could go through this together. Perfect. So, what we want to do here for this problem here is basically we're going to find the line of best fit. So we're going to go ahead and hit the stat key here. We'll go over to edit, and let's put these in as our lists. So we'll hit clear and enter. We'll hit clear and enter. And we're going to go ahead and put these into our lists. So means for us to go ahead and just take some time, put these in. Okay, so I put in all the values here for our X values, and I'll put in the Y values here. That's the stock return. So let's see what happens. This is negative. Got to put in the negative key. 8.12. 2.75, 4.96, 10.41, 7.26. Okay. So we have our list 1, we have our list 2, list 1 being our compensation, millions of dollars, and then the stock return there. Perfectly fine. Alright, so we're going to quit out of here. We'll hit second in mode to quit out of here. We'll hit the stat key here once again. Go over to calc. We're going to go down to number 4, which says linreg ax plus b. X list will be L1. Y list will be L2. Go to calculate. Alright. Now, I know this is correct because we have an R value here of negative 0.1955, which is what it says in the problem. So, to confirm that you put in the numbers here incorrectly, you make sure that it matches the R that they actually put into the problem here. Okay, so if it matches that R, you're in great shape, and those numbers you put in the list are perfect. Okay. Now, what's most important here is this A and B. That's going to be our most important part here, because this is going to reflect our line of best fit. So let's go ahead and write that in at the very least, based on what we see. All right, so what we have here specifically is we have y is equal to, and so here's kind of the thing about this. Okay, I'm not going to round here in the middle of the problem because what it asks you to find the line of best fit, but it doesn't ask you, it asks you to round to 1 decimal place, but it wants you to do that at the end of the problem. So to make sure I get the most accurate answer possible, I'm going to write the decimal all the way out, just to be on the safe side. You never know. So 0.8722840.436 x plus 31 plus 31.9903 7458. What is x? Kristen asks. So x here is going to be representative of the CEO compensation. According to the context of this problem here, will be the CEO compensation. So if we go back to our, darn it, I want. All right. Second. So to answer your question there, Kristen, that will be this, the compensation millions of dollars. That's what X is going to be because that was our X in our chart. Okay. So one thing to, okay, so this is where you have to be a little careful there, Kristen. The compensation here was in millions of dollars to start with. So it's not going to be 15 million, the number. Okay. Instead, it's going to be just 15 because X is already defined as in terms of millions of dollars. So I want to pick X is equal to 15 here. I want to figure out what that is, and then I also want to figure out what happens when X is equal to 25. All right, so since X is predefined to be millions of dollars, that's why I'm just going to leave the millions part out in that case. And I'm just going to plug in 15 into this function, and I'm going to plug in 25 into this function. So let me go ahead and do that here really quick. Okay, so the first one here for X is equal to 15, once I plug it into this line of best fit, is I get 18.9. I think they want 1 decimal place. Yeah, they want 1 decimal place. So I get 18.9 here for this first one. And all I gotta do is do 25 for the second one. And for 25 here, I get 10.2. And there we go. We got both of our answers here for our problem. Perfect. Any questions about that one? Hopefully that isn't too bad. Hey. Nope. See, trying to keep it as easy as possible. Doesn't have to be super hard. Just takes a little bit of time here and there. But I think you get it. Okay, good. Good. You can always watch these replays here, just in case, Megan. Just in case. I know this stuff here was this stuff here was more recent, but I'm like the chapter 8 stuff I know was from a while ago because that was like 3, 4, 5 weeks ago. You got the wrong answer. Okay, let's put it in the calculator here. I entered it into my manual calculator here, so Again, I didn't round. I rounded only at the end here, so here I have. Oh, your answer was 17.4. You got 19. Okay. So I don't know what your numbers were. Yeah, the homework numbers are going to be different. So mine's is different than what you have on yours. Okay, so that's going to be a little different. But I did negative, like I'll show you what I did on my calculator here. So I did negative 0.87722840436 times 15 plus 31.99037458. And then that's where I got the 18.9 from here. And then I basically just put in the same entry again as I did the last one. And just changed that to 25. And there I got 10.2 as my second one. That's how I was able to do both of those pretty quick. So one of the things I recommend that you do for that problem, Kristen, is to write down the entire thing here carefully on like a separate sheet of paper or something like that. That way you know what numbers you're plugging into the calculator. And again, don't forget to also look at your questions there, because the numbers are going to be different than what's going to be on mine. So on mine they asked for 15 and 25, but your numbers could be different, just because the homework and the tests always mix up numbers or whatever. So to be fair. So go ahead and give it another try and see if you can get that down. You just realized you mixed up the x and y. Your parabola is... Oh, yeah, that's kind of a problem there. Your parabola is sideways. When you get your equation for your parabola, I can help you find your maximum for your maximum or minimum for your parabola. So get an equation for a parabola, and then you can easily find the maximum or minimum for your parabola once you have that, Aiken. You just got to tell me the quadratic equation that you get from that. Is it CDA PSG tonight? Oh, yeah, I will watch that actually. What time is that on? Is that on at 7 tonight? That'll be like 1 o'clock my time. Oh, you missed a number in L2. Oh, okay, that's the problem. Oh, no. Yeah, you missed that one number. Yeah, check your list, like, double check your twists. Oh, in 2 hours, okay. Okay, so yeah, like at 8 o'clock, 8 o'clock, 8 o'clock, UK time. Well, I know you're in Dubai, so a little different for you. So for me, it'll be at 2 o'clock, 2 p.m. Central US time. I don't know what time it is in Dubai, though. 11. Ooh. I'm not sure anybody can really beat City this year. I think City's too deep this year. I don't think even PSG could beat City this year. It's gonna be pretty hard. To beat City over 2 legs is really, really hard. Like, they're already running away with the Prem, so it's like, well, they've already put the rest of Europe on notice. So well, I think there's going to be a lot of people who are going to be pretty salty about City even playing in the Champions League because of the punishment that was handed down last year that got overturned, I think. So and of course the European Super League. The very, very poor European Super League. I don't know why you think that's a good idea. That's terrible. Absolutely terrible. I would never thought that. I never would think that there would be a time where you'd have a break. Okay, that's not a very fair statement to say. The UCL is the Super League. The UCL is, but the one thing is that the Champions League, you have to earn your way in. And I like the fact that even if they're group stages, smaller teams can still break their way through to earn a spot in the Champions League. So like if the season continues and let's say West Ham makes it into the Champions League, then that's a feel good story that West Ham even made it into the top 6, made it into the Champions League spot. Like, I mean, that's exactly why the Champions League by far and away is much better than any European Super League with no relegation. It makes absolutely no sense. That's why Leicester City winning it in 2015 and 16, was amazing because they made it to the Champions League and they earned it. Yeah, exactly. People like underdog stories. People like when teams earn their way there. Okay, so the residual here. So what you need to do is, give me a second. The residual here is going to be the observed value minus the model value. This is when you use line of best fit. Okay. So let's say, for example, here, Megan, that you had, say, let's say your line of best fit is like 3x minus 20, or let's say plus 20, whatever. Okay, let's say your value that you observed here is like, let's say your actual observed value here is x is equal to 4, and let's say somehow you got 30 as your observed value here. So whatever was in the data set, maybe x equaled 4, you got 30 as your observed. So basically this is your observed value. So if you want to find your residual, it'll be your observed value here, which will be 30, minus, and then you plug in 4 into your line of best fit to see what you would get underneath your model. So 3 times 4 plus 20 is equal to 32. So here it'd be 30 minus 32, and your residual here would be minus 2 as a result. So that's how you can get your residual there. That's how you can find the residual there using the data set and the line of best fit with the X value that you were given. You fixed the missed number and I got the same exact... Okay. Fixed the mixed number and I got the same exact A and B value. What? What? How do you get the same exact A and B value? What? So confused. Yeah, I'm confused too. How do you get the same exact A and B value? What? If you change the numbers, that would change A and B. What? Yeah, you. Okay. That's so weird. You know what, Kristen? Just do another problem. Just do the. Get it wrong. Just hit similar problem, and do it with another data set. Just do it again since you're doing the homework problems. So just try it with a different set of numbers. I don't know what's going on with that, but it shouldn't be like that. Just try it with a different set of numbers. You're gonna boggle your mind. I don't know what's going on, to be honest, because I'm not sitting there next to you. But it shouldn't be like that, that's for sure. Sometimes that can happen. Be fair. Yeah, just try a similar question. Forget those old numbers. Let's try it with the new batch numbers. And this time go very carefully, one by one. Enter in those numbers exact, okay? I do that sometimes with some of those problems. Be like, you know what? Forget this. Puh. 6-0 to Chelsea in the first game. You mind? Of course you're not gonna mind. Yeah, read that again. Yeah, as long as you don't mind. You know what? Underdog stories are the best. Underdog stories are the best. I think one of the best underdog stories is Brentford. Brentford's a good underdog story as well. I love the Brentford story. That's one of my. I'm looking forward to seeing if the FA Cup stories. Yeah, the FA Cup stories are great. People who make it up into the, with Marine this year, right? Chadwick. Oh wait, yeah, wait. Wasn't that Anthony Hopkins, right? I think so. I don't. Even if Brentford doesn't win, Aiken, the fact that they've made it all the way up to the championship is even amazing enough. And they've done it with the shoestring budget and some statistical, some stats and stuff like a Moneyball-esque type of thing. It shows that you can run a football team, and you can still thrive with a football team that has a limited amount of funds and resources. Like I think it basically destroys the idea. They're without a win in 8 games, something. Yeah, they could have won the league. And you know what? That's fine. Look, if they hit a wall, they hit a wall, right? Leipzig's the same. Yeah, absolutely. It may come to a time where you may see strides in more statistical analysis, right? Teams that have big money that spend big, well, that may not be necessarily the formula to success. There have been lots of, as you know, Aiken, there's been a lot of busts in terms of transfer deadline days. So, it's like the same in baseball. Not every trade is going to be great. Not every splash of cash is going to be the best. You got to retool your roster every so often. It's the same thing as if the Chicago Cubs as well. You have a great roster, but they need to retool their roster ever since their championship run in 2016. They're gonna need some. They need some time. They need to probably retool their roster. They've traded away some key pieces. I wouldn't be surprised that if in the middle of the year they start by the trade deadline here in baseball, they're going to have to trade. They're going to probably trade away most of their assets and probably not re-sign a lot of guys who have been on the team for quite a long time. I'm not going to be shocked that a whole rebuild process needs to happen. So, and sometimes you need to start over, build up new player capital, new young player capital, and kind of start working your way up. Much the same way as Chelsea did. Same idea. Problem, I got 19.1 instead. Okay, hold up a second. Kristen, what problem is that in 4.2? You know what problem that is? What number is that? I want to see whatever this problem is. 2? Okay. Let's take a look. What is this problem doing to you? Alright. Alright. Yeah, so this is the same problem here. Alright, tell me what you're... Alright. So, do me a solid here, Kristen. I want you to click on the compensation and stock performance data thing. Okay? And why don't you on Discord here send me a screenshot of your numbers, okay? And I'll work on it with you together, okay? So if you go ahead and put that on the Discord there, you can go ahead and post your numbers there, like on a screenshot or something, and then I can take a look and see if we can get the numbers that it wants. Like, I want to take a look and see what your numbers are, because I don't know what your numbers are per se. But if we can see if we can suss out, oh yeah. Sorry. Yeah. Just a second here. There you go. Click on that link and then you'll be invited to the Discord. There you go. Okay, so you should get 2126 to 2127. Alright, so here's, alright, let's put that down. Alright. This problem here for a second. Alright, so I'm going to put this on the calculator here directly. And let's see if we can replicate these answers here. Okay. Alright, so hit stat, go to edit, clear out these lists. Alright, so 25.96, 12.98, 19.1, 1.71. Okay, so I got 10 values in there, perfect. 6.21, 30.44, 32.7, 79. 862. Okay. Remember to put that negative key in. Not the minus key, but the negative key. Don't forget about that. Have to use that negative key. 2.55, 4.2, 0.96. Okay. We have all those. All right. I'm going to go ahead and hit second in mode to quit. We'll go ahead and hit, go to calc. Go to linreg ax plus b, x list, y list. That's perfectly fine. And here we get negative. All right, so we want to make sure that R is correct, and R is correct. Okay, so 2.2, negative 2.22, negative 0.2127, pardon me. All right, so this is what we get for A and B. We have this absolutely correct. No, the negative key is not the same as the minus key. No, they are not. On a calculator, the negative key is separate than that of the minus key. If you put minus in terms of like a calculation, like 33 minus 15, okay, fine. But if you need to put like -5, you actually need to hit the negative key. So they're two different keys, minus and the negative key. So it'll give you a syntax error if you try the -5 using the minus key. You actually have to put in the negative key. That also is applicable on the TI Inspire as well. Okay, same numbers, perfect, okay? Now, again, Kristen, one of the most important things that you absolutely need to do is you need to write this whole thing out. You're gonna use this entire number here, okay? So we're gonna get negative 0.970995 x plus 33.6392308. This is our line of best fit. Now the numbers that we need to enter in here, let me go back to your Discord here, Discord screenshot. We're going to put 15 and 25 in here. So we're going to pick x is equal to 15 and x is equal to 25. So we're going to find two separate values here, putting it into this line of best fit that we have here. Okay. So let's see what happens when we plug in 15. So I'm going to do it exactly as I see here. Get negative 0.97. Second here. So to put 97096799955. I'm going to multiply that by 15 plus 33.6392308. All right, so here I get 19.07, so 19.1. Okay. Okay, now I need to take a look at that. All right. So you enter that in exactly. Fair enough. Check something here then. Okay. Unless they did. Alright, blah, 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 blah. Let's see what they did here. Oh, okay, okay, I see, I see. I see. Okay. Alright, I see. Oh yeah, I forgot about that part. Okay, okay. Okay, 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 okay. Alright. Now I see what's going on here. Okay. Alright, so let me go back here for just a second. Alright, so there's one thing that we have to keep in mind here that I totally had neglected myself. Alright, and that is, actually, let's go back here for just a moment. I'll go back to the actual problem here. So notice that says R here is negative 0.2286. Okay? So, what they did was here specifically is they asked a question here. That question here specifically is this a good linear model between X and Y? Okay? So we asked that question there when we did chapter 4 here. And so we're going to need this second part here. So we had a sample size here of 10. And we said as long as the correlation coefficient R, the absolute value of that, is bigger than this critical value, then it does have a thing there. Okay, so let me point that out here in this case. So if remember, if the absolute value of R here is bigger than that crit value, then a linear relation exists. Okay, we did talk about that here. Now, if we did it in this case, in this particular case, let's take a look. We have a sample size here of 10. Okay. So since we have a sample size here of 10, all right. Since we have a sample size here of 10, then we just have to check, does the absolute value of, what do we get here? Negative 0.2286. Is negative 0.2286, the absolute value of that, bigger than the critical value here of 0.632? Because that's our sample size here of 10. Now the answer to this is no, it's not. All right. So because the answer of this is no, right? Definitely not. So because the answer to this is no, they decided, so there's no linear relation, all right? So my fault was not looking at that part. Now because there's no linear relation here, all right, we cannot use the line of best fit. So what they decided to do is, because you can't use the line of best fit because there's no linear relation, then basically we use an average of the y's. That's all we're going to do. So use the average of the y's instead. Okay, that's what you're going to do here. So let's go back to our table here for just a moment of values. So the average of the y's here, specifically, we're going to add up all these y values here and divide by 10. So let's do that. I'm just going to take 5.53 plus 30.62, 31.7. Oh, actually, wait, these are not, sorry, hang on. These are my values. Let me use your values, Kristen. So in your values here, 6.21, 30.44, 32.17, 79.29. Oh, I'm hitting enter. Hang on a second. It's supposed to hit plus, and I keep hitting enter. 6.21, plus 30.44 plus 32.17 plus 79.9 plus negative 8.62 plus 2.55 plus 4.2 plus 11 plus 6 plus 11.35. And we'll just divide that by 10. And here we get 17.3, which I believe was your answer there in that problem. So that should get us to 17.3. Okay, and then that should be applicable to both parts. So try a similar problem again, but this time go through this one here. And I'll say the same thing here to Megan and Cool Dad. Same deal. Oh, Megan left, so I just have to tell her, fill her in about that part there. But yeah, that applies to this one here as well. Yeah, so that's what we have to do is I forgot about that part there. We do have to associate R with the critical value to see if there's association. Yes. Yes, that's correct. I wonder why we're coming up. No wonder why I keep trying to use the linear model, but I can't use the linear model if there's no association, which totally blanked out of my mind. So that's correct. You have 3 formulas, Aiken. What's your quadratic equation? What's your equation for your Those are 3 lines. What are Those are the same. Those are 3 lines. That's a line, Aiken. So a quadratic equation would be of the form if you have a parabola, every parabola has a quadratic equation. It should look like ax squared plus bx plus c. What you gave me is a line. So there's a difference. You gave me a line. Parabola is going to look like this, right? Or this, right? But what you gave me is just a straight up line. What you gave me is something that looks like this, or this. This would be like ax plus b. Because finding a max or min, yeah, this is the line of best fit. But you mentioned parabola. So I was like, a parabola, I'm thinking this. I'm thinking these guys. Unless you're thinking of just a line of best fit where it just increases or decreases by whatever, according to the model that you just pasted. Okay, what exactly does your question say, Aiken? First, type out your question exactly as it asks, and then we can clarify exactly what it wants. Because I'm not so sure about which direction I should go into unless we... You put it in the Discord? Okay. Let me go ahead and take a look then. Alright. So, X values, Y values. Yeah. Okay, I see what you used there on your Okay, I see that. Oh wow. It's a heck of a that line of best fit is so bad. A line of best fit is so bad. How could this function be used? Oof. Let me show you what I have on my screen here. Oof. A line model is terrible for that scatter plot. Oof. No, I don't think that. I think that was the intention of the question, I think. How could this function be used to find the maximum and minimum of the variable? Well, if I'm right about this, I can't say it's going to be the best R here necessarily. That R is going to be pretty awful. Yeah, that's just calculations and stuff. How could this function be used to find the maximum or minimum of the variable? I mean, it's not the best function to really be using for the maximum or minimum of the variable, to be fair. The regression line is actually pretty bad. If I would put anything, it would be okay. Check that. What would be the best one for this? Be x cubed, right? Check that. It'd be like cubic thing. Parabola isn't sideways now, at least. Thank you for working out my problem. One more question. For this problem, does it matter if a positive or negative slope? No, it doesn't matter. It's just positive negative slope, remember, just depends on the, again, the rate of change, right? That's what slope represents there, Kristen. R is always supposed to, the absolute value of R. So note here, Kristen, is the absolute value of R. So it's the absolute value of R has to be bigger than the crit value. All right. So you have to first take the absolute value of R there, and then find out if that's bigger than the critical value depending on the sample size. So that's what it will come out to be. Okay. How could this function be used to find the maximum or minimum of the variable? I mean, you have another parabola. I mean, this is a line. All right. All right, go ahead, Aiken. I'm kind of curious what you got there. You can go ahead and post that on Discord if you have a thing there. Or actually, if you have like a screenshot of what your question is specifically. I want to see what the context of this question is. All right, cool. All right, cool, Kristen. All right, pretty flat. I'll put the questions in below. Okay, in the square. Okay, cool. All right, construct tables in the scatter plot. What does the scatter plot look like? Okay. Got a known function. Oh, okay. All right. Now this starts to make sense. Okay. Now this makes sense. Okay. No wonder why we're having mixed paths here. All right. So, so it says, all right. So let me explain what's going on here, Aiken. All right. It says construct a table of values and the scatter plot, which you have. Okay. So let's just take a look at the picture you sent me from before. You clearly did that here. Okay. You have the scatter plot right here. That's all these yellow dots that we see here. Perfect. Okay. What does the scatter plot look like? Now, that second question here is actually going to be the biggest key to doing the rest of this problem, okay? That question there guides you through the last 3 questions after that. Now, why am I saying that? The real question I have for you, Aiken, is that what exactly does that look like? Does that look like a line to you? Like if you look at the scatter plot there, right? Does that look like a line to you? Yes or no? So just by looking, no. Okay, so we're not going to use the line of best fit. All right, line of best fit is out because that would be a line, and that clearly doesn't match the shape of that scatter plot, right? A repeating wave. This is where we have to be a little careful here. It is a repeating wave, but it is not necessarily follows a parabolic shape. A parabolic shape. The issue with the parabola is this, okay? And let me point this out here for you. The issue with the parabolic shape is that in a parabola, there's only one curve in the parabola. Okay, that's the problem. There's only this one curve here. Okay, there needs to be a second curve here. Again, it's going to look something akin to this, right? This is what it should look like, correct? So in fact, in this case here, Aiken, yeah, right? It shouldn't look like a 1 curve. It should look like a 2 curve, according to what we have here. So in this case here, what does it best reflect? This actually reflects a cubic regression model. Now that is something, this here would be like x to the third, ax to the third plus bx squared plus cx plus d. That would be looking something akin to this. So if I were to go on this graph here, all right, so let me, yeah, that's just the midpoint. Why would I do that? All right, so try it with a cubic regression here. Let's try it that way. There's a calculator for that. I don't know what your numbers are specifically, so I'm going to send you a link here for you to enter in the numbers here again. Okay. Okay. And let's see what numbers we get for this, because I don't have all your numbers, so. Yeah, so you can see that the cubic function looks like that if you want to know how I figure that out. So, which looks exactly like your scatter plot. see if we got something going on here. Okay. Oh, wow. That's actually really good. All right. That looks pretty good to me. Ooh. I like that too. Really, really good. All right. Excellent. All right. So there are a couple of things that we can certainly take away from what you posted here in Discord. I'm going to go ahead and drag it over here. Take a look at it together. All right. So first and foremost, we now have the cubic regression equation, right? So if this is our cubic line of best fit, we can actually figure out what that will look like here on a graph. Not sure on the cubic function because I'm doing temperature over the past 12 months. Shouldn't it just repeat itself then? Well, in relation to that, if we go back to our questions here, that would kind of be indicative of number 5 here. What part of the function would indicate the time interval in which one complete cycle occurs? That would be over the 12-month interval. So part of the function would be the x. Okay, for example, that would be a 12-month cycle, and then kind of again to make one complete cycle. So you'd look at x there specifically from say 1 to 12. Unless unless x has a different representation that I'm missing here. And these are 26 months, is that correct? Or is these 26 days? Oh no, that's every 15 days you said, right? I believe. Yeah, this is just a touch over a year if it's every 15 days. I did 1st of April. Yeah, okay. Yeah, so it's every 15 days. Okay, so it represents the full year, and then the temperature in this case for each one specifically. All right, seems fair. Seems absolutely fair. Back to your questions here. All right, so we know what the scatter plot looks like. It looks like a cubic function. Could the known function be used to model the data, find the function? Well, we just found the function here using this. Look at that correlation. That correlation is 96%. That's really, really strong, okay? So I would say a cubic function here is definitely your function du jour. Okay, 100%, that's the answer there for number 3. And you found the function already. How could this function be used to find the maximum or minimum of the variable? Well, you can use the cubic function here to find the local max or local min. So if you find the local maximum and local minimum of the function between 1 and 26, okay, then you can easily find, if you find so the answer here to number 4 specifically is to find the local max and min of the cubic regression function. To find, so that's, so if you want to use that there, again, the cubic regression function looks akin to this, right, as you see on the picture. So you're just basically trying to find this little guy and this little guy down here. between 1 and 26. So where's the local max and local min? According to the cubic regression function, that's where you're going to find your maximum and minimum, since your scatter plot roughly associates with that at the end of the day. What part of the function would indicate the time interval in which one complete cycle occurs? So that would be the x function here. Yeah, so it'd be the vertex on the cubic function, correct? We call it local max and local min because it's within a particular interval, right? I don't want to say maximum or minimum here, like, because I don't want to talk about it in absolutes. Otherwise, because the graph technically will stretch to like infinity, and that's obviously not like reflective of what we want, right? We want it to be like a local max and local min. So if we're talking absolutes, obviously it stretches to negative and positive infinity, which doesn't make sense for what we want. So we want it to be like that repeating cycle, right? So that's why I refer it to as a local max and local min. So it's that small vertex there between those two values. If you want to call it a vertex, it's that small vertex between these two values, and a small vertex here, between those two values. So if you want to call it that way, if that's what you're comfortable with, Aiken, then we'll go with that. But again, I'm falling it between two specific values here. Yeah, so that's why I use local max and local min. So like this here would be my local max, and this here would be my local min. All right? Does that make sense? So if I had my picture here, let me go back to my picture here, like a generic picture, right? Yeah, so if I have my just picture here, here's my local max, because technically this stretches down to infinity. This goes up to positive infinity. My local max. This is my local min. Okay. I want to say hello to those people who have come in here to the stream. I see a few people here. If you have questions, please feel free to ask. It's more of a question and answer for those people who have with stats and whatnot. So certainly please ask, and we'll be more than happy to go over questions with you. Don't forget, if you're here with the second class, that's perfectly fine. Remember that all the homework has been reopened here, and that the last test there has been posted then as well. So 9,45 is the local max. Is that according to... Let me take a gander there. Oh, according to the table. Yeah, I didn't see the table. Let me see. That one. Yeah, so that would be the local max of that. That'd be the max of that particular cycle. That's correct. Yeah, but that's not, again, the local max is just within that one little cycle, right? So that would be that local max of that cycle. Correct. Okay. Cool. So that'd be the, in this case, in our full cycle here, that would be the largest value here. But if we wanted to find like the maximum value, it would be around, say, the ninth 15-day cycle, Yes, that would be correct, right? Yeah. Now, they're not asking you to find those specifically because, again, those are specific data items in a data set. Okay? Take a look at the question here very carefully, Aiken. Okay, so be a little careful about this. It just says, how could you use this function to find the maximum minimum? So it's not asking you for the maximum minimum here. Those are pretty easy based on the data set for that particular data set. It's just how can you use it here? So the answer to that question for number 4 is find the local max and min of that function, and you can approximate about where you can find the maximum. The maximum temperature is in this, this little area, and the minimum temperature is going to be in like this little area here. So between within these 15 days, you're going to get the maximum temperature for the year. Within these 15 days, you're going to get like the minimum temperature for the year. That's what it's asking you here for number 4, just to be clear here. Okay, so not asking you actually for the specific values according to the question here. So I just want to be clear with you about what it's actually asking for number 4. I hope that makes sense. Again, if you've just come into the stream here for the second class, so it is how to find the local max or min like I did, or just in general? Just in general, to find the local max. Yeah, not the way you found it here via the data set, but you would find a local max or min, using the cubic function as your backdrop. So you can use you could use a calculator to find the local max or min of a function, or you can use what's that called again? Not roots. There's another way to find that there. Kind of blanking out right now. There was another way to find that off the top of my head. So I'd say I find the highest and lowest y value in the table. No, Aiken. How could this function find the maximum? Okay, yeah. Yeah, you could use so you could use the calculator to find the local max and min of the cubic line of best fit or another. Okay, you could say that for number 4 there. Why am I blanking out on that? I shouldn't blank out on that. Oh right, you have to use the first derivative test. Oh yeah. I don't know if that might be beyond the scope of the course, to be honest. That's right. I don't know if you do it. I don't know if this is for calculus, Aiken, but if it is, then you could use the first derivative test to find local max and min. But that may be beyond the scope of the course. I don't know, Aiken. So that's a calculus thing. So if it is, then you could just use the calculator to find the local max and min of the cubic line of best fit, to be fair. There's the answer number 5, by the way. There we are. Okay. Since it's cubed, it's going the wrong way anyway. Wait, what? What does that even mean? Aiken, what? What does that mean? Oh yeah, leave out the line of best fit. The cubic line of best fit is what you want. Cubic line of best fit. A line of best fit is terrible, but a cubic line of best fit. Cubic line of best fit, okay. Line of best fit, no bueno. Okay? Cubic line of best fit is the answer to your question, but not the line of best fit. Big difference between the two. So that would answer all the parts. We have part 1, part 2 pretty easy. Part 3, we found the cubic line of best fit. We know the function. All right, number 4, find the local max and min on the cubic line of best fit to find out where the maximum minimum of the variables are going to be. And what part of the function would indicate the time? That would be, again, as I put down here, one complete cycle uses the x variable from 1 to 26. Okay, since 1 year is our cycle here for this particular problem. And that should be the answer to your question. Hopefully that helps. For X on the calculator, do I press it on the keyboard? I don't know how to use the Inspired at all, Aiken, so I'm not sure, actually. Like, the Inspire is kind of like way above my head in terms of actually how I would use it. So I don't know. Like, most of the time I use the TI 8384, so the Inspire is just like the super strong calculator, and since I don't really use it at my job, most of the time it's 8384. So I actually couldn't tell you. Actually couldn't tell you on that one there. I don't know if that's the same or not. So hey JD, how do we find the table that has all of those percentages? I forgot what it was called. In reference to what, JD? I'm gonna need to be a little bit more specific. Are you talking about the confidence intervals and the critical values that were associated with that? It's just a straight line upwards when no, wait, how? How is it a straight line upwards when you filled in the cubic regression equation? No, definitely not. Okay, you know what? I'm going to do it on my calculator here, Aiken, because I know for a fact that is definitely not true. Okay, that is definitely not true. 100% that's definitely not true. It's not x. Like, Aiken, hold up a second. Go back here for a second. This function is what you need. So you need to have it as y equals ax cubed. So it has to look like this. It has to be ax cubed plus bx squared plus cx plus d. Okay? That's what you should have. Like, okay, so you need to zoom out a little bit is what you need to do. You need to zoom out because yours is way too far zoomed in. I can see it, but make sure that it's correct there. 1152 minus 0.6515, where it's 7.18727. And then make sure you have the plus 20.6003. Make sure you zoom out and then see what you have between 1 and 26. Because on your Inspire here, Aiken, all I see is between 1 and 10. So it might be too zoomed in right now. So zoom out a bit. You think? Okay, let me check here really quick. That was an answer there, JD. All right, JD. Got an answer. Wait, can you can't find the okay. Probably the problem. So JD, do you mean this table here? Is this the table you're looking at here? Your critical values with the percentages? If this is what you're referring to, then this may be what you're looking for, JD. All right. Said it was in the book? Okay. You get a plot, please? Check that here. That's right. Like that, please. Okay. Why is that plot not showing up? That's weird. Right? What I would like. This too. Yep. Sure. Stand. Zeus. There we go. Yeah, that's better. Okay, there we are. Alright, so JD, you gotta tell me, like, is it gonna be the critical values that you're thinking about, or are you thinking about, what other values are you thinking about? Because then these would be the 3 values you need for, like, confidence intervals to find, like, the sample size and stuff like that, JD? That would be what I'm referring to here? Because I'm, like, I'm kind of thinking about, there's a lot of different tables here that we could look at specifically. So I want to be specific. Okay. Cubic reg. Okay. There's something from chapter 4. Okay, give me a second here then. I think I know what you're talking about. If you could look that up while I'm doing this, then that would be helpful for me. Hey, Rossless, Rose. I'll just call you Rose. Rose, thank you for the follow. Appreciate that. Appreciate that very much. I hope you're doing well. Let's see, this should be x squared. Be plus 7.1827x. Why the heck would you put that? X. Alright. Plus 20.6. Alright. That's what the cubic line of best fit actually looks like there, Aiken. So what you see on the screen here is exactly what the line of best fit will actually look like there on the graph. I use the TI-83 or 84 here, but this is essentially what this will look like here, and you can see how closely associated that that line of best fit is in comparison to our data set that you gave me there. Yeah, isn't it smooth, right? Looks pretty smooth. So from our stat plot to how we found our line of best fit, our cubic line of best fit, and then I mapped it out, and then that is exactly how it would fit with the scatter plot there. And as you see, they're very closely associated with each other. And that would hopefully confirm all the answers that we had there from parts 1 to 5. So that should answer fully your question there at the end of the day. Your graph on the Inspire should look similar to this. Okay? You may have it too zoomed in, I don't know. But I put it as a plot, stat plot on the calculator. So I have the stat plot there to put it on a scatter plot. And then I plotted the actual cubic line of best fit on top of that, as you can see there on the screen. So if you zoom out, and then if you have the same thing that I do, that is similar to what I have on my screen there, Aiken, you should have it. Okay? Now let me go to chapter 4 here. You only saw the first line. Yeah, the only part that you saw are these screen count. This is a... So this is the TI-84 Plus. This is like the calculator you get as an app on your computer. I pay for a license for this through my school. So, but you can also this is the 8384. I got it as a license through the school. You can actually buy the license yourself as just a regular person. It's like $100 or so, but that's how you buy the relationship. That's how you buy the license for that. I'm trying to see in chapter 4 here. It wasn't here. All right, let me try the next one. So, are you talking about R squared? JD, you gotta tell me what's going on. I'm just hoping we can get some answers here. I can help you out here, JD. If anybody else has any other questions, please feel free to ask. I'm gonna try and help you as best as I humanly possibly can. I can show off this. Let me see if this gives you a friendly reminder here. A second. Go to the e-text. Because I have some tables here that we may or may not have used. I don't think we used any tables really in this class, but just to be on the safe side. Okay, so there is this table. This table here usually comes with what does the correlation coefficient mean? That means it's how strong a relationship there is between X and Y. Okay, so how strong a relationship is there between the time of the year and the temperature, like the days in the cycle and then the temperature, right? So X was the time of the year, and then the cycle, the date, and then the temperature there. So it's a 96% correlation between that. And using the cubic line of best fit, by the way. Using the cubic line of best fit, there's a 96% correlation. It's specific to the cubic line of best fit, so by the way. So don't forget about that. Was it this Aiken? Or not Aiken, was it this JD? Sorry. Was it the critical values for the correlation coefficient? Is that what you're referring to there, JD? Because this usually has a link in the problems that we usually do in chapter 4. So I'm just wanting to make sure that if that's the one. Ah, okay, cool. Yes, so you should have a link on every homework problem and even on the test problems. The thing that we use this for here, JD, is if we want to compare to see if there's, say, a linear relationship between R and this critical value. So the way it goes here, and let me go ahead and put this on the split screen here for a second. The way this goes here specifically is, just as a good refresher here, is if the absolute value of the correlation coefficient is bigger than the critical value that we find on this table. And remember, the critical value here that you find on this table is dependent on the sample size. So it depends on the sample size, all right? All right, so if your sample size is 10, then your critical value here would be like, say, 0.632. So if the absolute value of R here, absolute value comes first, then we have a linear relationship exists. Okay? So it only applies is if the absolute value of R is bigger than that critical value. A linear relationship. If it doesn't, then basically, I did a problem like this earlier here today. If it doesn't exist, like we had this problem here in 4.2 specifically, where that wasn't the case, and then we had to do it a different way. So I'm going to show that off here for you. All right, because I wouldn't be surprised if you may have run into the same issue there, because we ran into the same issue as well. So that was on section 4.2, number 2. So you're probably trying to use the line of best fit for this problem here, but then where it wasn't getting it correct, for example. And you're probably saying, well, where did they come up with the other number here? Well, in this case, go ahead and show off of this particular problem here for you. In this case, what they did was they first compared the absolute value of R. So we say, is the absolute value of 0.2286 bigger than the critical value here? Now, the critical value here with n being equal to 10, if we go back to our little table here, for example, back to our table. Just a second here. No, I didn't put the table away. Oh, there it is. Okay. So with n is equal to 10 here, our critical value here is 0.632. Okay. So let's ask ourselves here, is the absolute value of negative 0.2286, is that bigger than 0.632? Yes or no, JD? Yes? What's the absolute value of 0.22? So you're saying 0.2286. Remember, the absolute value here, read that carefully, JD. Absolute value just makes it positive, right? That's what we do know. So let's rephrase this. Is positive 0.2286 bigger than 0.632? Let's rephrase that. So what you're saying is that 0.22 is bigger than 0.632? Is that true? No, it's not, right? All right, so read that carefully. It says if the first number is bigger than the second number. Well, either way, it would not be true, right? Even if it was negative, a negative number is always smaller than the positive number. So even with the absolute values making that positive, it's still not true, okay? Either way, the answer here would be no, okay? So in this case here, there's no linear relationship. So because there's no linear relationship here, what they decided to do instead was they did the average of all the y values here in this problem. All right, that's all they did. So we just take the average of all the y values. So that's all they did. So just take the average of all the y values. So all they did was they did this, and no joke, this is all they did, is that they took this and they said, okay, let's enter in all these numbers here. So 5.53 plus 30.62 plus 31.27 plus 80.18 plus, and then a negative here. So let me put a negative really quick. Negative. Negative 8.21. Don't forget to use that negative key. Plus 3.04 plus 4.63 plus, keep adding, plus 11.08 plus 4.44 plus 11.45. Okay, and then we divide that by 10 because that's going to be 10 values. So the average here was 17.4. For my problem here anyway, it's 17.4. So let's check it out and see if that happens to be true. Okay, so if I put in 17.4 for this, instead of using the line of best fit because there's no linear relationship, then it'll tell me that's the right answer. And the same, you get the same exact answer for the next part as well because there's no linear relationship. You're just taking the same average with the same numbers, and I get it right. So that's what I'm doing here for, say, section 442, number 2, in relation to that. So I just want to point out that one little difference here. I have to thank Megan and Kristen for bringing that up here earlier on today. So I want to bring it up with you since you asked about that chart and where it's relevant. So still important to point out here so that way you're not caught unawares. Right, nothing. Okay, good, good. Just making sure, make sure your bases are covered there, JD. If it has a linear relationship, then use the line of best fit. If it doesn't have a linear relationship, go ahead and use the averages of the y values, and you're good to go. Okay? Hey, you have any other questions about that? Make sure that we have our bases covered at the very least. Anybody else have any other questions? Please feel free to ask. Can I graph the other two formulas? Oh, we've been allowed. No problem, Aiken. Of course. You know I'm always willing to help you. The other two formulas, are you talking about the line of best fit and the like a parabola? If you're referring to those two, Aiken? Want to be sure that that's what you're referring to here. Okay. Yeah, I could do that. You'll see how they don't fit. Like, you'll notice right away that they absolutely won't fit. But that's a cubic function there. That's a cubic function here. I can graph that function. I don't have a problem doing that, but yeah, I can certainly just put it on here. Let me write that down. You wanted me to put it with the scatter plot? Okay. Is there a difference? Is there a different data set to go with that cubic function, by the way, Aiken? Or is that the same one? As I doubt that would be the same one. It looks like a different cubic function. Together? Okay. Sure. I can do that. Alright, if it's a different data set, then I need to plot it out again, so... Can you put it on Discord, the data set? Like, I'd be more than happy to put it out with the data set that it's associated with. No, but you just told me there's a different data set to go with this, Aiken. So if you have a different data set, post that in the Discord, and then I can map out the new X and Y chart. Go ahead and map it out at least. Alright, so here's what you gave me. There you go. That's what the data set that we had from before. Okay. Want to have the other two? All right. So the blue one here is our cubic line of best fit. This red one here is the one you just gave me, and yeah, now we'll just need a third one there. And then I'll go ahead and put that on the graph, and then put it together. And change that color. If anybody else has any other questions, please feel free to ask. I'm here to help everybody. So, surprisingly, I've been very busy just with lots of questions here today, which is good. Is there a faster way to solve question 4 on 8.2? Check that. Should have a weird shape, okay? Send it over, Aiken, and we'll take a look, yeah? So, see if, okay. You said, okay, sorry about that, I missed that. Let's check that. Send it above JD's. 079 x cubed 785 x squared. How does it do that? I know you want us to have the arrow because bad habits are bad. Okay. So this one will be in green here, Aiken. So we'll take a look at the graph there. So that's the graph there for that one. So it's very different than that of the others. Actually, let me check that one more time. You got negative 0.0179? Okay. If you give me negative, then that's why the shape is what it is. Alright, that's fair. Here you go. The shape is very different because the initial coefficient is negative, so okay. Oh, it greens the humidity? Okay, that's fair. I'm gonna switch, actually, let me switch this around. Homework 8, 2, and 4. Alright, here we go. Hey, no problem. You know I'm here to help, my friend, as always. I'm always here to help. You know me. I not only have a love for hashtag, but I have a love for helping out people with maths. Anytime, my friend. As best as I possibly can. Exit polling popular technique to determine the outcome of the election prior to results being tallied. Yeah, Elkin, you're always free to ask, by the way. So you're always welcome and you're always free to ask. Suppose a referendum to increase funding and education on the ballot in a large town, voting population over 100,000. Exit poll of 300 voters finds that 153 people voted for the referendum. How likely are the results to your sample if the population proportion of voted town How likely are the results of your sample if the population proportion of voters in the town in favor of the referendum is 0.49? Based on your results, comment on the dangers of using exit polling to call elections. Okay. So the probability that more than 153 people voted for the referendum is blank. Okay, so in this case here, we have a population proportion of 0.49 according to this JD. All right, so in this instance, we have to use, in this case, a normal CDF. Okay, so it's not really of course we're going to use the calculator to go ahead and figure this out, guy out here. But there's a couple things that we'll need to go ahead and talk about here, first and foremost. But we need to first, the first thing that we actually need to do here for this problem specifically is this. Is that we're dealing with a sample size of n here, JD. Our sample size here is 300 people. All right. Now we said, okay, how much is above 153? We'll use this 153 here in just a moment. Okay, but we're given a mean here of 0.49. All right, and they want us to find the probability that more than 153 people voted. Now, where are we going to use this 153? We're going to first figure out what the proportion of people of 153 over 300 is going to be as a decimal, okay? Because we're going to be dealing with percentages throughout this problem. So if I do that here, this is going to equal 51% or 0.51. So in reality, this question is asking you, we want it to be above 0.51. So we're going to use normal CDF here. All right. And so let's go to our calculator here. Good, second in vars. Go to normal CDF. I wanted to get to the submenu there at some point. There we go. All right, so we're going to do the normal CDF here. So normal CDF, we have a lower. Our lower here is going to be 0.51. Someday it would be good. Enter that in. Thank you. 0.51. Our upper is going to be 1 up to 100%. Then we have our mean here of 0.49. Now, the last part here, JD, that is important is going to be our standard deviation. Our standard deviation is different in this section. The standard deviation here is a formula. You'll have to remember here from section 8.2. That's the square root of p times 1 minus p divided by n. So in this case here, this is going to be the square root of 0.49 times 1 minus 0.49, and then divided by 300. Okay? So that's what I'm going to be putting here for this last part, is the standard deviation here will be the square root, let me go ahead and put this in here, the square root of 0.49 times 1 minus 0.49. I'm going to divide that by 300 since that's how many people we asked, and then we'll close those parentheses. Important here, JD, you do have to close the parentheses here for that. Okay, very important. Okay. So now let's go ahead and have the calculator do that in our stead, and let's see what we're... All right. So over here we get 0.2442 is our answer here. Let's check it out. Where'd my question go? Right? Okay. So the probability is 0.2442. All right. Let's check our answer, and that's correct. Good. All right. Now they want us to comment on the dangers of using exit polling to call elections. All right. The result is unusual because P is extreme, then more extreme than the sample proportion is less than. This is unusual. All right, so the result is not unusual because if the result was unusual, it would have to be less than 5%. Okay. So the result is not unusual, so it's going to be B or C. So thus, probability is P is equal or more extreme than the sample proportion is less than 5%. This is unusual for a wrong call to be made if the exit. Result is, okay, I gotta read that again. The result is not unusual because the probability that P hat is equal to or more than the extreme sample proportion is less than 5%. Okay, I think it's B. Don't know. Yes, that's true. I'll just guess C and see what happens. I think it's C. Yeah, okay. So the result is not unusual. That's true. Thus it is not unusual for a wrong call. Okay. Oh, whoops. That says thus it is unusual. This says it's not unusual. Okay. Whoops. I read that wrong. All right. My bad. So the answer here was C. It's not unusual because it's not less than 5%. It was 24%. And it's not unusual for a wrong call to be made if exit polling is alone considered. So that part is that would be your answer there for the second part for 8-2, number 4. All right. Any questions about that? Hopefully that was pretty straightforward. No worries. If you have any more questions, anybody has any more questions, JD, anyone, please ask. You know that's what I'm here for, so. Feel free to ask if you have anything more to want to get to know. So busy. I love it though. Super fun. I get to have fun. Ooh. So the lower bound and the upper bound there are dependent on whatever the probability asks you, right? So the lower bound is going to be like, you go from 0 to 100 there, JD, okay? So Since you go from 0 to 100 there specifically, so if it says, say, less, let's say it said it was more, it said more than in this case. So we went from 0.51 to 1. So that would be your lower bound, and upper bound would be, if it says less than, so let's say it said, let's say for example here, it said P is less than, X is less than 51%, for example. Then your lower would be 0, and your upper would be 0.51, because it'd be like 0% to 51%, for example. So it really depends on this this inequality that you have here, whether that be less than or whether that be bigger than. But in any case, you're going from 0 to 100%, and either you're going from that percentage to 100 or 0 to that percentage, or somewhere in between. So remember that lower will always be the lower of the two numbers, upper will always be the higher of the two numbers. But at the end of the day, it just depends, right? If you see how we did the actual problem here on the calculator, notice I put 0.51 and 1 here, so 51% to 100%. So I hope that makes sense there. Let me see if Hey, how's it going, Wade? Your mom was getting the second vaccine and hey, man, I totally understand that, Wade. 100%. I hope your mom will be. You might want to want to maybe be sure to take care of your mom today. All right. The second vaccine usually is rougher than the first. So make sure you have like some like Tylenol, or like, you know, something that'll help with that stuff there. She should probably feel the effects within 12 to 18 hours. So I hope you got your vaccines all ready to go there, Wade. So hopefully you're feeling good as well. My cool dude. Mom gets the 2nd, 8th of May. Yeah. So if your parents are going to go get it and they may have the effects there, then yeah, be sure to hopefully take care of them. It's gonna be a little rough for like maybe a day or two. So that's how it was with me personally, as I rested in bed for quite a while, to be perfectly honest. Like I was completely out of it for like a day or two over the weekend when I got my second shot. So wouldn't shock me that your parents or yourself go through the same thing. But that's again the shot working as intended. Okay, so that is not not to say those are bad things. Those are things that are supposed to happen when you get your second vaccine. Okay, so don't want to freak you out or anything like that. That's perfectly acceptable. Get, you know, fatigue and nausea and fever and those kind of things. Okay. Let's see, Maggie, are you there? Maggie, are you there? Maggie, I hope you're there. Yeah. I don't know if Maggie's there or not. Yes, okay, good. I sent you a whisper there, Maggie. Um, uh, need to talk to you really quick here, so. Hey, no problem, Wade. It's all good, my dude. All right. I hope to see you next week. If you're gonna pop on off here, then yeah, and see you next week. Sent you some whispers. What is the story? I don't remember if we actually did that. I don't remember. Well, I'll have to figure that out. 9-1 on the first question. Okay. Yeah, how was it? Was it good? Is it as good as advertised? Hopefully it was. I know a lot of people love that series. Maggie, do you know where the whispers? Maggie, do you know where the whispers are? Question mark. Okay. It's like, wait, I'm sending you stuff. I'm trying my best. Rip certain character, he just... I watched his sub, because yeah, of course you watch it subbed. Subbed is better than dubbed. Alright, so you want a 90% confidence interval for this? So did you use, did you use, did you use one prop Z there? In this case, you go over to tests and you go to one prop Z int. That's letter A. And then we enter in our X is 75, N is 250. Our confidence level here is 90%. Calculate that out, round to 3 decimal places, bada bing, bada boom. Winner, winner, chicken dinner. 252.348. Got it. Got it, baby. That's how we do 9-1 question 1. There we go. Let me take a look at something here, Maggie. You didn't follow what I said, what I did? JD, bro. You're so mean. I haven't even watched the movie. On the help me solve it. Ooh. Oh my goodness, that's hilarious. Let me check this here. Yeah, okay. Alright, that's what I thought. Alright. I thought so. I went too fast? Oh, sorry about that. My fault. All I did was use one prop zint. That's all I did, and then I plugged in the numbers, and then I got my answer, and then I was done. And that's all I did. Yeah. That's that. I swear that's all I did. What is this? So, I just hit the stat key and I went over to tests and I went down to letter A. You know, about to get says one prop zint, and then I found it, and it was like that. Ashley, are you there? Ashley! I hope you're there, Ashley. Ashley! I haven't even seen the series, to be honest with you. I know everybody says the series is amazing. I have never watched even the series. I've been very well behind. Ashley, are you there? I need to talk with you. Are you there? I guess not. They're in here, but oh. They respond back. Hopefully they come back at some point. I know you're still here. You know, I need to put some emotes. I need to make up some emotes, man. Shoot. Maybe I should maybe I should start making up some emotes and stuff at some point. I haven't really expanded this channel much in a year, just because usually this is just a math-related channel. So I mean, I haven't had really a necessary need for emotes of some type, but you know, maybe make up a few emotes would be okay. I might recruit somebody to hopefully help me make up some emotes. Some math emotes would be good. Maybe to kind of go along with my whatever image that I bring up here. I don't even know. I have no clue what image I actually bring up on here on this channel. So yeah, I've made like I've made like 100. over the year, I've made like $100 or so, $150. So, I mean, it's not like a lot, obviously, but I'm not looking for necessarily money. And that's over a year, but again, I don't do this for, you know, and if somebody says I want $150 back, I'm like, I'll be happy to give you $150 back. I don't got a problem with that. You know, I'll be like, dude, that's cool with me. In a year's worth of time. But I don't do it for the money. I do it because it's I don't do it for the money or subs or whatever. I just do it because, you know, obviously we do it for the class, but you know, I also do it for funsies. Teaching is fun, so I get to sit here and I get to have fun and I get to goof off for a lot of things. For me, it's more of an achievement than a reward. Okay, yeah, yeah. The thing is, like, it's the reward. Yeah, I mean, that's why I've never been focused on like, oh yeah, you got to give me some subs, you know, you got to do this and that. Like, I understand that for a lot of people here on Twitch, the subs are really, you know, kind of like the money making ventures and stuff, right? But for me, it's not about the subs. For me, it's about like spreading the education part here. So, you know, just fostering a good community when it comes to something like that. Ashley, if you're there, please please respond. So, Ashley, Ashley, are you there? I hope Ashley's there. I just put that there. She might have me on mute, so. Alright, let's take a look here at the screen. We got a national survey of 1,500 adult citizens found that 16% dreaded Valentine's Day. Yeah, I'm with that 6%. It's Valentine's Day. Sadness. The margin of error for the survey was 12.8 percentage points, with 85% confidence. Explain what this means. All right, so we have a margin of error of 12.8 percentage points. So we just have to figure out 12.8 percentage points, and we have 16% the dreaded Valentine's Day. So all for this one is basically we take 0.16. Oops, let me go to the main screen here. Sadness. We're going to take 0.16. We'll go ahead and subtract it by 12.8%, which is 0.128. So our lower end is going to be 0.032. And we have 0.16. We'll add that to 0.128 to see what our upper end would be with our margin of error. So 0.288. So I would say there's 85% confidence that the proportion of adult citizens that dreaded Valentine's Day is between these two guys. It looks to be letter A. That would be it. Yes. Letter C makes no sense. And letter B makes no sense either. So it would be letter A. Yes. That is correct. And that's how we can answer number 4 on section 9.1. It's as simple as that, my friend. JD knows what I'm talking about. She has the whole story. She knows. JD kicking ass, taking names. I guess Ashley has. It's fine. You're not that tough? I don't know about that. I have full confidence that If we had met in person, you'd still kick my ass. You know, that would be probably true. 100% true. It'd be like, ugh. You'd probably be like, hey, Professor Chibs, bam, straight to the face. And I'd be like, oh! I'm like, yeah, I deserve. Be like, yeah, I deserve that. I was a bad math professor. I've been doing everybody wrong for a long time. Face punches. Face punches are acceptable from all my students. Hey, Aiken, thank you very much for stopping on by, my friend. You know you're welcome anytime. If you got any more questions, I'll be more than happy to help you out, my friend. Have a great time, man. Time is it? Oh, okay. It is that time. Alrighty. Good beans. Alright. Well, I guess this will probably be the end. What is the drink? The drink of the day was like was a frappuccino coffee. That was the drink of the day. I finished it off. Add some water as well. So just kind of going back and forth here with a couple of drinks. But I've been at this for 3 hours. Holy cow! I can't believe 3 hours just went by like in a blink of an eye. Holy smokes! What does coffee do to me? It does good things. I'm not gonna lie. All right. JD, everybody else here in the chat, I think it is a time that I go. We're kind of running a little overtime here, but I know you guys have more questions, so you know there's going to be more time for you to ask those questions, and I'll certainly have the time to answer those questions. So don't forget that the last test there is due on the 9th of May, but I will have the final made up here by next week. So I'm going to be making an announcement here on Monday in regards to the final exam and talk about that in a very great detail. All right, everybody, that will take care of it for today. Thank you so very much here today. I really appreciate JD, Aiken, everyone here who stopped by in the chat. Thank you so very much. I hope everyone has a very wonderful day. All right, stay safe, stay healthy, and most importantly, everybody, stay sane. All right, have yourself a wonderful weekend, and we will see you here next time on Monday talking about the final exam and more questions. All right, take care of yourself. I will hopefully catch up on some Demon Slayer. All right, you have a wonderful day. All right, all right, everybody, have yourself a good one. All right, take care, everybody. Bye.